Hello everyone, my name is Christina and I will be presenting a proposed mechanism of the E2 reaction. This is the given reaction. As we can see, I've identified the nucleophile, the electrophile, and the given product in this case. I will also later discuss electron flow and any regiochemical preferences. In this case, I've highlighted the nucleophile here, which is defined as something that is electron dense. Here, this is sodium hydride, which acts as the electrophile. The electrophile is something that is electron deficient, and it will react with the nucleophile to form this alkene here. One important thing to note is that the E2 mechanism also acts as an acid-base extraction, so you could also consider this sodium hydride acting as a base. Now on this third slide, I've drawn out the mechanism here. So this means that the base, the sodium hydride here, will extract the beta proton, and the beta proton is located at a carbon that is one carbon away from the leaving group. Once this is done, these electrons in this carbon-hydrogen bond will come down here to form a carbon-carbon double bond, which is later seen here in the product. As a result, the carbon and tosylate bond will break, causing the tosylate to leave, and it will form a tosylate ion. We are then left with an alkene, which is here, a tosylate ion, and a water molecule. It is important to note that an E2 mechanism always requires a strong base, such as seen here. So, additionally, it's also important to understand why we're removing a beta proton and not an alpha proton. Is here I've switched it to a chair conformation, so it's easier to understand as to why a beta proton is extracted and not an alpha proton, which would be located here. So a beta proton is extracted because the electrons from this bond must be able to form a pi bond, specifically with the carbon that contains the leaving group. The carbon with the leaving group is going to lose a bond, so it must gain a bond in exchange. This is the pi bond, as we can see here with the tosylate ion gone, floating around here. Now this wouldn't work with an alpha proton because it would have nowhere to go. As we see here, it wouldn't be able to go anywhere. Now an E2 reaction proceeds via concerted mechanism, which means that everything happens at once. This is similar to an SN2 reaction, and it is also important to note that just like an SN2 reaction, an E2 reaction is bimolecular, which means that the substrate is weakly coordinated to the base and the leaving group at the same time. So in this reaction, we also have two cyclohexene rings, which you can see here, and you could see here originally as well. I just switched this to a chair conformation, so it's easier to understand why this reaction proceeds the way it does. Now, in order for the E2 reaction to occur, the leaving group, which is the tosylate here, you can also see it here as well. It must be anti to the hydrogen that is removed on the adjacent carbon, which we can see here. They're both in axial positions where the beta hydrogen is axial up and the tosylate compound is axial down. This means that they're directly opposed to each other, and this is also known as being anti-periplanar, which is a key characteristic of the E2 mechanism. As we can see, this will occur when both groups are axial to one another, just as I explained. So as you can see Here is the sodium hydride, and it's extracting the hydrogen beta to the leaving group, causing it to collapse, forming this pi bond here in our product. And as a result, our tosylate leaving group will leave and form an ion out here in solution. And this is how the reaction occurs. Thank you for listening.